In our last lecture, we talked about potential energies and springs. And in this lecture, I want to talk about energy conservation and conservative and non-conservative forces. So, what are conservative and non-conservative forces? Basically, conservative forces are forces that keep energy within the system, and non-conservative forces are forces that transfer energy out of the system. So examples of non-conservative forces might include something like friction. If friction is present, then the work done depends only on the starting and the ending points. Depends not only on the starting and the ending points, but also on the path taken. So here you see two paths that the box could take to get from 1 to 2. If it starts at path 1 and goes in a straight line to path 2, then that gives it a shorter path. If it starts at path 1 and goes in a curved path around into point 2, then it goes in a longer path. If it goes in a longer path, then that gives friction more distance over which to act, and that'll suck more energy out of the system and transfer that energy into something like heat or sound. So that force doesn't conserve or keep energy within the system. If you look at some examples of conservative and non-conservative forces, some that you'll deal with in Physics 1103 and 1104, conservative forces include gravitational force, the elastic force for springs, and the electric force, which you'll learn about in Physics 1104, or the force between charged particles. Those are conservative forces. Non-conservative forces include things like friction, air resistance, drag, tension in cords, rocket propulsions, and pushes or pulls by a person. So those are all examples of non-conservative forces. So conservative forces keep energy within the system. Non-conservative forces transfer energy out of the system. Conservative forces are path independent, whereas non-conservative forces are path dependent. They take more energy if the path is longer. If you want to apply the energy equations for non-conservative forces, then you'll see that any energy that's lost from the system, be that in the form of kinetic or potential energy, that energy will go into the work done by non-conservative forces. Let's think about the sign here for a second. If there's a loss in the energy of the system, then your change in kinetic energy or your change in potential energy, or both, will be a negative number. So you'll have a net negative on that right-hand side of the equation if energy is lost from the system. And that energy goes into the work done by non-conservative forces. If you think about your equation for work for a second and think about friction, your work is equal to force times the distance times the cosine of the angle in between the displacement and the application of the force. Remember that friction always acts against the direction of motion and against the force, which means the cosine is going to be the cosine of 180 degrees, which is a negative number. So you have negative numbers on the left-hand side and the right-hand side, indicating a loss of energy for the system. I'll deal with how to do energy conservation problems when you have a loss in the next lecture. But in this lecture, I want to ignore non-conservative forces for now and just introduce the concepts of how to do these energy conservation problems. So if you ignore friction and non-conservative forces, then you can say that for that system, energy is conserved. The change in the kinetic energy plus the change in the potential energy equals to 0. Okay? If we define the mechanical energy as the sum of the kinetic energy and the potential energy for that system, then you can say that if the system goes through some sort of change and you ignore any non-conservative forces, then the energy after the change, which I'll call E2, equals the energy before the change, which I'll call E1. And that's just because delta E total would be equal to 0, because you've lost nothing to kinetic or potential if you've only got conservative forces. So it'll be equal to some constant value. All right? So let's examine in just sort of a conceptual way right now conservation of mechanical energy. For example, let's think about dropping something. Okay? To drop something, you have to hold it up at some height. When you hold it up at a height above your origin, that implies that you have gravitational potential energy, or mgh, or mgy. And then what happens is, if it's released from rest, it starts off with all potential energy, and then all of that energy is converted into kinetic energy when it reaches the ground. By the time it reaches the ground, it's going as fast as it's going to go. Let me show you an active figure for this idea. So here we have a hand releasing a ball, okay? And before the ball is released, you can see these are plots, bar graphs, of kinetic energy, potential energy is PE, and total energy is TE. If you release it from a height of 25 meters and then I press start, what will happen is the ball starts out slow and then goes faster and faster as it reaches the ground. We learned this in Chapter 2 when we did one-dimensional kinematics. So by the time it reaches the ground, all of that total energy has been converted from potential into kinetic. I can reset that and show it again. And all throughout the fall, you can see that the total, if you summed the kinetic and the potential energies, the total would still be the same. The total remains the same, and it just gets exchanged. It gets converted between potential and kinetic energy. All right, so that's the idea there. You can also apply this to any number of problems. I'll do some examples later, but if you ignore friction and drag, then you can consider things like pendula and roller coasters and all that kind of stuff, okay? So if you ignore friction, for example, the speed of a roller coaster will depend only on the height that you started at, okay? And then it'll speed up as it goes into the dips, and then it'll slow down as it starts to go back up. And that's all about conservation of energy. Now, if you've got springs or some kind of elastic force, then you have your elastic potential energy, and that's converted into kinetic energy. All right, so if I pull up the active figure for that one, not that one, sorry, hang on, this one, okay? So over here, I show a plot of the potential energy for a spring, which is equal to 1/2 kx squared. Remember that x is the displacement of the spring from its equilibrium position. So if it's at its equilibrium position, then it's got no potential energy, which is where it is now. See, I haven't started it yet. I haven't given it a push. So it's at x equal to 0. Then when I give it a push, see, I've given it to the complete compression of the spring, I've given it its max potential energy. So you can see I've now transferred energy into the system by pushing on it. Now it has a certain amount of energy and it's all potential. Then if I release the spring, what happens is it oscillates about that equilibrium position, okay? And then as it oscillates, it goes from kinetic to potential and back again. Most of the time it's at some intermediary place where it's got kinetic and potential energy, okay? But if it's at max extension or compression, then that's all potential energy. And if it's at the equilibrium position, well then the spring potential energy is 0, which means all of the energy is kinetic. And you can see that if you ignore friction, then the motion would just continue on forever, and the mass would oscillate back and forth about that equilibrium position once I've given it that push. Okay. Now, there's other forms of energy that we probably won't get to in this class. Electric energy we'll get to in Physics 1104, but we won't touch on nuclear energy. We'll talk about thermal energy in Physics 1104, but we won't talk about chemical energy. Okay? All of these forms of energy, though, it's important to realize that they all obey conservation of energy. So even if energy is lost from the system via a non-conservative force, it's going to be transferred out of the system. It doesn't go away completely. It's not created or destroyed. It's just transformed from one form to another. Okay? Now I want to do some example problems with real number crunching on these problems. Okay, so the first one that I want to do is a simple pendulum. So here we have a bowling ball on a string, okay, a bowling ball hanging from a rope of length L. And then what you do is you pull it away from equilibrium by an angle and you release it and you let it swing. If you ignore friction and air resistance, then we can consider this to be a conservative system. And what the problem asks you to do is express the speed of the ball in terms of the length L and the angle, which we call theta. All right, so where on all these energy conservation problems, the first question you should ask yourself is, where am I going to put my origin? Okay, where am I going to put my origin? Because remember that your potential energies are going to be defined with respect to your origin. For gravitational potential energies, like you're going to have here, it makes sense to put your origin at the lowest point, okay? And then all heights are measured with respect to that lowest point. The lowest point for this problem is going to be where the bowling ball is at the bottom of the swing, okay? Then it's at its lowest point, okay? So that's where I put my origin. And then you also want to ask yourself, what kinds of energy am I going to be dealing with here? Well, you only know equations at this point for two types of potential energies, gravitational potential energy and spring potential energy. Okay? Well, there's no springs in this problem. Okay? So you know it's going to be gravitational potential energy at this point. And if it's somewhere in its swing other than at the max angle that you pull it to, then it's also going to have kinetic energies. So you're going to have kinetic energy and gravitational potential energy. Therefore, I've written the equation here, 1/2 mv squared plus mgh is equal to my total energy. And that's always going to be the case for this problem. Remember, that's my mechanical energy, the kinetic plus my potential. And then for these energy conservation problems, we know that that mechanical energy is going to be conserved. Now, how are we going to write our height h, okay, above our origin, which is the lowest point of the swing? Well, here in the drawing at the right, I show a simple pendulum. So in this one, the pendulum's been pulled back to some angle, and then you can see that that lifts it a certain distance h above the origin. What distance is that? Well, if your string is a length L and your angle is theta, okay, then the vertical axis here is adjacent to the angle that you pulled the pendulum back to. So you would use a cosine function, cosine of theta. And L cosine of theta gives you the length of the right triangle that goes from the top where it's attached down to the height where the bob is, and then there is your hypotenuse of your triangle will be the length L of the string. Okay? This is assuming that it's not doing some weird thing where the rope loses its tension and kind of bends. So we're assuming that it's a nice taut rover string. Okay, so how do we write h in terms of that? Well, the total length of the string is L, and then h would be L minus L cosine of theta, okay? Which is that L cosine of theta is that distance down, which is one of the legs of that right triangle. So h is L minus L cosine of theta. At the highest point in the swing, so let's say at some time t is equal to 0, you pull it back and you release it from rest from this maximum angle. That will give you your maximum energy, okay? At that point, when you release it from rest, there's no kinetic energy, and you've given it all the energy it's ever going to have in that system when you pull it back and give it that initial height h. So you can say that your total energy at that point, since the kinetic is 0, is mg L minus L cosine, and I'll call it theta max for the maximum angle. And then after you let it go, after time t is equal to 0, it'll swing back and forth, and most of the time it won't be at the maximum displacement, so you'll have some sum of kinetic and potential energies. So what you can do now is say that I'm going to call E1 my energy at time t is equal to 0 when I pull it back to its maximum displacement and release it from rest. So I've got my energy at that time on my left-hand side. mgy, or mgh in this case, is mg times L minus L cosine theta max, and kinetic energy is 0 at that point. Now at some later time t, some random time when it's not at the max angle anymore, it's going to have a sum of kinetic and potential energies. So the kinetic is 1/2 mv squared, and then the potential is mg L minus L cosine theta. Remember here, theta, say if theta max is 30 degrees, then theta could be at some intermediary angle, like 10 degrees, which is less, okay? So there you go, E1 equals E2. Now the problem asks you to solve for the speed, okay? Your mass appears in every term, so you can cancel that out, all right? I've done that in that second step. And it also wants me to write the speed in terms of the length and the angle. So I've moved everything that's not a speed over to the left-hand side of the equation and expressed it that way. Now, in order to solve for the speed, I multiply through by 2 to cancel out that 1/2, and then I take the square root of both sides to get the speed. And I end up with an expression here, the square root of 2g times L minus L cosine theta max minus 2g times L minus L cosine theta. Now I've combined terms, the 2gl and then the minus 2gl, those are going to cancel out. And then I rearrange things a little bit, and I get my speed is equal to the square root of 2gl times cosine theta minus cosine theta max. All right, so that's the solution of the problem. Okay, the next problem I want to do is about a spring. So here I have a horizontal spring attached to a wall and it has a spring constant of 870 newtons per meter. If there's a 1.2 kilogram mass permanently fixed to the spring, all right, and then you pull that block to a position 5.4 centimeters from equilibrium and release it from rest, then what's the speed of the block when it's in some different position, say 2.7 centimeters, half of the maximum displacement. Okay, so yet again, first of all, what kinds of energy do I have? Well, this is all in a plane, right? So there's really no change in gravitational potential energy for this system. It's not going up or down a hill or going up and down. So I can ignore gravitational potential energy because that's going to not change. The only other kind of potential energy that I know about right now is springs potential energy. So I'm going to have elastic potential energy, and I know that. And then I'm also going to have kinetic energy if it's at some point other than the maximum displacement of the spring. So I'm going to have kinetic and elastic potential energy. So those are my two types of energy. Where am I going to put my origin? Well, the place that it makes the most sense to put the origin for a problem involving a spring is at the equilibrium position of the spring, right? So that's where I'm going to put my origin, here at x equals to 0. All right, so I know that in general, my mechanical energy is going to be 1/2 mv squared plus 1/2 kx squared, because that's the equation for elastic potential energy and kinetic energy, and my mechanical energy is equal to the kinetic plus the potential. Okay, now I want to figure out what my total energy is. So it tells me in the problem what the max displacement of the spring is. At my max displacement, I'm releasing my spring from rest from that position, and so my kinetic energy at that point is 0. Okay? Also, at maximum displacement, your kinetic energy is always 0. Why? Because you're turning around and going the other way when you reach your maximum displacement. And so at that point, at least for a split second, your speed has to be 0, so your kinetic energy is 0. So at time, say t is equal to 0 when I start the clock at its maximum displacement, I've got my total energy is equal to my spring potential energy at that maximum displacement, 1/2 kx squared, which is 1/2 times 870 newtons per meter times 0.054 meters squared. If I solve for that, then I know that the total mechanical energy that my system has is 1.27 joules. Ignoring friction or dissipative forces, it keeps that same amount of energy for the rest of the time. So now I can set that 1.27 joules, my energy E1, equal to the energy at some later time, right? At the later time, I know what my displacement is, okay? And I also know that I'm going to have kinetic energy at that time because it's at some midpoint, right? So I have 1/2 mv squared plus 1/2 kx squared equals 1.27 joules. I don't know what my speed is, but I can plug in for my mass, 1.2 kilograms, and I can plug in for the spring constant, 870 newtons per meter, and I can plug in for the displacement at that later time, which I know is 2.7 centimeters or 0.027 meters. If I plug in for all of that stuff, I can multiply through by 1/2 870 0.027 squared, and then subtract that from both sides. And then I get 1/2 times 1.2 kilograms times v squared is equal to 0.95 joules. Now I just multiply by 2, divide by 1.2, and then take the square root to get my speed at that point, and it's 1.26 meters per second. All right, for my final example problem, I want to do the loop-de-loop problem. Okay, so here you have a bead sliding without friction around the loop-de-loop. And the bead's released from a height, okay, and the height is 3.5 times the radius of my loop, which is shown here in the picture as capital R for my loop. What's the speed at the top of the loop is the question, and then how large is the normal force on that bead at the top of the loop if the mass of the bead is 5 grams? Okay, so for this problem, what kinds of energy have I got? I've got kinetic. As it starts to fall, it's going to speed up. And I've got gravitational potential energy because it's not always at the same Y position. Okay, so those are my two types of energy. I don't have a spring here, so I can ignore that one. Where do I want to put my origin? Well, I want to put my origin at the lowest point. The lowest point here is the bottom of this loop here at the bottom, right here. Okay? So that's where I'm going to choose to put my origin. So in general, I have kinetic plus potential, which is 1/2 mv squared plus mgh, and that's at some random time t. Now in the beginning, when the ball is released, I'm going to consider that to be my 0 point, okay? When the ball is released, it's released from rest. So that means that kinetic energy is 0 at that point. So my total energy is equal to mgh. And I know what h is. It's 3.5 times the radius of my loop. So I'm going to plug in for that. My energy is mg times 3.5 times r. Okay? That gives the ball its energy, which is then held constant through the rest, ignoring friction. Now, what it asks is what the speed is at the top of the loop. Okay? So that's going to be at some later time, and I'm going to have some kinetic energy at that point because it's going to be moving through the loop. So I've got 1/2 mv squared plus mgh at that point, and h at that point is 2 times the radius of the loop, right, because it's at the top of the loop. So I have 1/2 mv squared plus mg times 2r is equal to mg times 3.5r, right? So I've set my energy as constant at t is equal to 0, and then when it's at the top of the loop, I set those two things equal for energy conservation. Now I can solve. I can move mgr times 2r, I can subtract that from both sides of my equations, and I end up with 1/2 mv squared is equal to mg times 1.5 times r. M appears everywhere, so I can cancel that out. Multiply through by 2 to cancel out the 1/2 and take a square root. And I have that the speed at the top of the loop is the square root of 3g times r. So I've solved part A. Now to find the normal force, I can't use energy conservation. Okay? I have to use the free body diagram stuff from the circular motion information that we learned earlier. So at the top of the loop, okay, I have two forces acting on it. I have the normal force, which is pointing downwards, because the loop is up here and the bead is here. So the loop pushes downwards on the bead to hold it in that circular path. And then I also have gravity acting down. So what you do for the circular motion problems, remember, is you sum up the forces in the radial direction, okay, and then set those equal to your centripetal force. The radial direction we define to be positive if it points in towards the center of the circle. So here we have plus mv squared over r, because that points in towards the center of the circle, is equal to m plus mg, because both of those point in towards the center of the circle. Now what I can do is I know what the speed is at the top of the loop. It's the square root of 3gr. So v squared would just be 3gr, and I plug in for that in my equation. So I have m times 3gr over r is equal to little n plus mg. Now I can cancel out the r that appears in the top and bottom of that equation on the left-hand side, and I have 3mg is equal to n plus mg. Move the mg, subtract that from both sides, and I have my normal force is equal to 2 times the mass times gravity. Now I know what gravity is. It's 9.8 meters per second squared. I know what the mass of my bead is. It's 5 grams or 0.005 kilograms. And so I can solve for what the normal force is at the top of the loop numerically, and I get 0.098 newtons. Okay? So that's a few examples, 3 examples, on energy conservation problems. We'll do more in class. I hope that helps, and I'll see you in class.